Good day everybody. We got a beautiful question. We are expected to integrate integral 0 to pi over 2 and the integrand is tan inverse of 2 times cos squared x divided by cos squared x times dx. Now this is a beautiful question and an elegant problem. So foremost, what I wish to do is I would like to apply the Feynman's technique in neutralizing this challenge. So for that I would like to define a new function. Let I of say sum p to be equal to integral 0 to pi over 2 tan inverse of, now this 2 is going to be my p times cos squared x divided by cos squared x times dx. So we got two variables, p and x. Now having got this, what I wish to do is I would like to exclusively state what we really want. So we want I of p when p is equal to 2. So actually we require I of 2. This is our goal. Now for this we also required boundary condition. Now setting p is equal to 0, what happens? We got I of 0 is equal to integral 0 to pi over 2 tan inverse of 0 times cos squared x over cos squared x times dx. Now 0 multiplied by cos squared x, that's going to give me, let me write it like this, tan inverse of 0 divided by cos squared x times dx. Now tan inverse of 0 is 0, so this is going to be 0 to pi over 2, 0 in the numerator times dx divided by cos squared x, which is going to give me 0. So this would mean my boundary condition is I of 0 is equal to 0. Now this is important. So having got that, let me now obtain d over dp. I'm going to operate both sides by d over dp of I of p is equal to d over dp integral 0 to pi over 2 tan inverse of p times cos squared x over cos squared x times dx. On the left this is I dash of p, on the right we got d over dp, so I'm pushing it inside. Now since we have a quantity involving two variables, this is going to give me dou over dou p, limit 0 to pi over 2 tan inverse of p times cos squared x over cos squared x times dx. Now cos squared x is actually treated as a constant, so that does not mean you can push it out of the integral operator, but you can actually bring it outside of the partial derivative operator. So that's going to be 1 over cos squared x times dou over dou p of tan inverse of p times cos squared x times dx. So this is 0 to pi over 2. Now we have to partially differentiate this quantity with reference to p. So this is equal to integral 0 to pi over 2 1 over cos squared x. So when you differentiate this, p is the main variable, right? So when you differentiate this, well, what you're going to get? You're going to get differential of this. So you have tan inverse of this quantity. So that would mean I would have to apply the tan inverse differential. So what is tan inverse differential? So suppose you have y is equal to tan inverse of x. Now you want to find dy over dx. So differentiating tan inverse of x will give you 1 over 1 positive x squared, right? So we will have to utilize this formula when you differentiate this quantity. But apparently we have inside or I would say tan inverse has got an argument involving p times cos squared of x, or I should say p times cos squared x. So we need to, instead of x, we got this entire quantity. So that would be the differential that we will have to use. So what I'm going to do is, let me get rid of that. In fact, instead of striking it, let me just, I don't want to strike it in between. Let me rewrite that step. So dou over dou p, I will have to differentiate tan inverse of p times cos squared x. Okay, so that is going to give me this differential is going to be, I'm going to utilize this formula. So it's going to be 1 over 1 positive, in place of x I've got p times cos squared x, this has to be raised to the power of 2, times I need to differentiate this quantity. So the coefficient of p is cos squared x, so just place cos squared x there. That is multiplied with d times x. So we need to be careful when we are operating with the partial derivative dou p. So this is fair enough, and I can cancel this cos squared, and I can actually use the space here. So this is now I dash of p is equal to integral 0 to pi over 2. What do we have? We got 1 over 1 positive p squared times, this is cos squared raised to the power of 2, right? That's going to be cos raised to the power of 4x times dx. So I hope you are able to follow what we have got. So this is what we have got. Now what are we going to do? We will have to utilize complex numbers. We will have to split this. Now how am I going to split this? Consider 1 positive p squared cos to the power of 4x. So can I rewrite this as 1 negative p times cos squared x, and I want to place a I there, right? Can I write this as 1 negative I times p times cos squared x multiplied with 1 positive I times p times cos squared x? Can I write it like this? So if I were to write this like this, let me go to the new page. So what happens here? I want to keep that in the frame. So this is actually 1 I into I. This negative into positive will give me negative, right? So I into I is going to give me I squared, and p into p is going to give me p squared. Cos squared into cos squared is going to be cos to the power of 4. But my I squared is equal to negative 1, complex numbers, right? So that would mean this is going to be 1 positive p squared cos raised to the power of 4x. So what we can do is, in place of this, we can substitute this. So let's do that. So I dash of p is equal to 0 to pi over 2 dx divided by 1 negative I times p times cos squared x multiplied with I times, or I would say 1 positive I times p times cos squared x. Now I'm going to use partial fractions. Okay, so utilizing partial fractions, I'm going to consider, let me just move this off, consider 1 over 1 negative I times p times cos squared x multiplied with 1 positive I times p times cos squared x. Now I can rewrite this as a over 1 negative I times p times cos squared x positive b over 1 positive I times p times cos squared x. So you have to cross multiply, you get 1 is equal to a times of 1 positive I times p times cos squared x positive b times of 1 negative I times p times of cos squared x. So this is what you've got. So now you will have to actually find the value of a and b. So what we are going to do for that is, we will have to make one of the terms to be equal to 0, and then we will sufficiently be able to actually extract one or the other, right? Our purpose is to get the value of a and b, so we will have to make one of the terms 0, and then that would subsequently give us a or a b. So let's do that. So what I will do, I will start with this term. So let ip times cos squared x be equal to 1. So if I were to take this term equal to 1, this one is going to get vanished. So I would get a of 1 positive 1. On the left I got 1, so therefore a is equal to 1 over 2. And by taking the other term, suppose if I were to take ip cos squared x is equal to negative 1, then this term goes away. So this is going to be negative 1, so negative of negative 1 is going to be positive 1. So this is going to be b of 1 positive 1. On the left is going to be 1. So therefore 2 times b is equal to 1 and b is equal to 1 over 2. So we got a is 1 over 2, b is equal to 1 over 2. So in place of this, I'm going to utilize this. So this is now equal to integral 0 to pi over 2, this term 1 over 2, and my a is 1 negative I times p times cos squared x times dx plus 1 over 2 over 1 positive I times p times cos squared x. This is what I've got. Now I can split this, right? I can split the operator inside or distribute the operator. So this is going to be 0 to pi over 2. On the left it's I dash of p, 1 over 2 times dx over 1 negative I times p times cos squared x positive 1 over 2 times 0 to pi over 2 dx over 1 positive I times p times cos squared x. So we got two quantities to be integrated, right? So what I would do is I would first consider this one. So let me take this as I1 and let me take this as I2. So I can assign here, let I1 be equal to integral 0 to pi over 2 dx divided by 1 negative I times p times cos squared x, and my I2 is equal to integral 0 to pi over 2 dx over 1 positive I times p times cos squared x. So two quantities are there and we would be integrating one at a time, and after integrating one at a time we would actually get the values for I1 and values for I2 and then make the substitution and then proceed on. So let's get it done. So first what I would do is I would just consider I1 to be equal to integral 0 to pi over 2 dx divided by 1 negative I times p times cos squared x. So I'm going to consider this. Now what I would do is I would multiply the numerator by secant squared x and divide it by secant squared x. So that is going to give me integral 0 to pi over 2 secant squared x times dx over 1 negative. Now just distribute secant squared x. So this is going to be secant squared x negative I times p cos squared x times secant squared x. That means secant squared x cos squared x gets cancelled, giving you I times p. Okay, so this is what we have got. Now I would like to actually make the utilization of the trigonometric substitution, that secant squared x negative tan squared x is equal to 1. So that would mean my secant squared x is equal to 1 positive tan squared x. Now let me just substitute that over here for the denominator. So this is equal to, on the left you have I1, so it doesn't matter. So 0 to pi over 2, in place of secant, you retain secant squared x as it is, but in case of the denominator you substitute it with one positive tan squared x negative I times p times dx. So rewrite this. This is 0 to pi over 2 secant squared x times the dx over tan squared x negative. You don't have to put negative, just place positive, just club these two together. It's going to be 1 negative I times p. So this is a beautiful value. Now we will approach this by making the following substitution. Let u be equal to tan x. Differentiate this. This is du is equal to differential of tan x is secant squared x dx. So this is equal to, don't touch the limits as of now. In place of secant squared x dx, I have got du. So just substitute du. In place of tan squared x, I got u. So just place u. This is raised to the power of 2 squared positive 1 negative I times p. Right. Now limits, when x is equal to 0, tan 0 is 0. When, let me write that down. When x is equal to 0, u is equal to 0, because tan 0 is 0. So when x is equal to pi over 2, tan pi over 2 is equal to infinity. Right. Sin pi over 2 divided by cos pi over 2. Cos pi over 2 is going to give you 0. And 1 over 0 is infinity. That's the reason. So 0 to infinity. That's a nice value. Now you got this. Now this is similar to integral dx over x squared positive a squared, which is equal to 1 over a tan inverse of x over a positive arbitrary constancy. So we will have to utilize that formula. Let me go to the new page. So this is equal to 1 over a, 1 over 1. In place of a, this is actually not, over here it's a squared, right? So over here we do not have a squared. So we just have 1 negative I times p. So what I wish to do is, I would like to place, if I can place a square root, because I need to write this as a squared. So it's root of 1 negative 1 I times p, 1 negative I times p squared. Right? If I were to do it like that, then I can have a squared there. In place of, I don't have to write it. In fact, I'm going to rewrite this. Okay, this is fair enough, but I'm going to rewrite this in this fashion. So this is equal to integral 0 to infinity. Let me rewrite it like this: du over u squared positive 1 negative I times p. I'm taking the square root, then I will place the square there. It's possible because a raised to the power of n times m can be rewritten as a raised to the power of m, the whole raised to the power of n, or a raised to the power of n, the whole raised to the power of m. That also goes for the values of m being, say, in a POQ form, or a rational quantity. So I can do that. So this I did this because of the fact that I got 1 negative IP. So it's square root and the square, they get neutralized. But then I want to make use of this formula. So I want to convert this quantity that you see here as this quantity. So that's only possible if I can exchange the position of 2 and 1 over 2. That's exactly what I have done. So if I were to apply this formula, then this is equal to 1 over a, and my a is this. So it's going to be 1 over root of 1 negative I times p tan inverse of x over a. My x is u divided by root of 1 negative I times p. So this is the all important value that I've got, and my limits are 0 to infinity. Okay, now we will have to deal this a little bit tentatively, or I would say a little bit carefully, because this is of the form, the most popular tan inverse of z, where z is a complex number. Now tan inverse of z as a representation. Now let me just write that, where z is equal to u over root of 1 negative I times b. This is actually a complex number. Now we will have to get a representation for tan inverse of z. Now I'm going to show that how tan inverse of z is obtained, right? So if I were to take tan inverse of z to be as, say, some omega be equal to tan inverse of z, then this would mean tan of omega is equal to z. So this in turn means my z is equal to sine omega divided by cos omega. But since we are dealing with complex numbers, my sine omega, we know that sine omega is e raised to the power of I omega negative e raised to the power of negative I omega divided by 2 times I, right? So we have a representation like that, 2 times I, and cos omega is e raised to the power of I omega, and this is going to be positive e raised to the power of negative I omega divided by 2. So if I were to substitute these things, therefore sine omega divided by cos omega e raised to the power of I omega negative e raised to the power of negative I omega divided by 2 times I. Now this goes here, so when I flip it, you get 2 over e raised to the power of I omega positive e raised to the power of negative I omega. 2 and 2 gets cancelled, giving me 1 over I. So you got e raised to the power of I omega negative e raised to the power of negative I omega divided by e raised to the power of I omega. You got a positive e raised to the power of negative I omega. So this is what you have got. Now on the left end you have z, so you can just place z there. So now what I would like to do, I would like to cross multiply. So if I cross multiply, I get z times I, because I is there, times e raised to the power of I omega positive e raised to the power of negative I omega is equal to e raised to the power of I omega negative e raised to the power of negative I omega. Now what you have to do is you will have to actually extract the value for e raised to the power, or I would say you would have to get the value for omega, right, the representation for omega. So what I would do is on both the sides I would like to multiply by e raised to the power of I omega, right? So if I were to multiply by e raised to the power of I omega, let me see what exactly I'm going to get. E raised to the power of I omega, so this is going to give me e raised to the power of I omega times I omega, 2 times I omega. This is going to give me a negative 1. This is going to give me e raised to the power of 2 times I omega. This is going to give me a positive 1. Okay, so I want to represent the quantity omega, right, in terms of z. Okay, so let me just distribute. Let's see how or what we are going to get. So this is going to be z times, let me have this I, I'm going to distribute z, so 2I omega positive I times z is equal to e raised to the power of 2 times I omega negative 1. Now I can bring this quantity all to this side, so let me use this part of the page. So this is equal to I times z times e raised to the power of 2 times I omega negative, this is brought in e raised to the power of 2 times I omega, and then I'm going to take this out to the other side. So if I take this to the other side, it's going to be negative I times z negative 1. I take e raised to the power of 2 times I omega. So let me rewrite this as e raised to the power of I times 2 omega is taken out. This is going to be I times z negative 1 is equal to negative I times z negative 1. So this is what I've got. Now as I mentioned to you, I want to extract e raised to the power of I times 2 omega. So if I were to push this down, this is going to be, can I rewrite this as 1 positive I times z. I'm taking negative sign out. Now this is coming down. This is going to be I times z negative 1, but I'm not happy with the way this is represented. So what I'll do, I'll take the negative sign out and rewrite it as 1 negative I times z. This is 1 positive I times z. You have a negative sign, so both the negative sign gets cancelled. So this is going to give me e raised to the power of I times 2 omega is equal to 1 positive I times z divided by 1 negative I times z. Now what is, can we actually take ln both sides? So taking ln both sides, this is ln of e raised to the power of I times 2 omega is equal to ln of 1 positive I times z divided by 1 negative I times z. Now ln of a raised to the power of b is equal to b times ln a. So I'm going to use this part of the space. So this is equal to 2 times I is there, I times 2 times omega is equal to ln e is equal to ln of 1 positive I times z divided by 1 negative I times z. Now can I utilize this fact, ln e is equal to 1? So ln e is equal to 1. So you have I times 2 times omega. So let me write this down as I times 2 omega. Ln e is 1. Ln of 1 positive I times z divided by 1 negative I times z. Now I want to push this 2 times I down to the right side. So therefore I get omega. Therefore omega is equal to 1 over 2 times I times ln of 1 positive I times z divided by 1 negative I times z. Now why am I getting omega? Now I need omega because omega is actually tan inverse of z. Now why do I need tan inverse of z? I need tan inverse of z because I got a tan inverse of z where z is equal to u over root of 1 negative I times b being featured as a quantity that I need to evaluate. So I did all these things to show you that tan inverse of z as a representation of, or in this fashion, 1 over 2 times I ln of 1 positive I times z divided by 1 negative I times z. So safely we are going to be utilizing that particular result. So what I will do, I will go to the next page and I will take this as a. Right, so this is equal to 1 over root of 1 negative I times b of tan inverse of u over root of 1 negative I times p. This is 0 to infinity. Now we know that tan inverse of z, we just obtained that, right? I'm going to utilize this, is equal to 1 over 2 times I ln of 1 positive I times z divided by 1 negative I times z. So this is what we are going to be utilizing. Now this can be rewritten as, just let me just move this off so that is out of frame. So substitute the value of z. So this is going to be, let me just calculate. So tan inverse of u over root of 1 negative I times p is equal to 1 over 2 times I ln of 1 positive, in place of z you substitute u over root of 1 negative I times p divided by 1 negative I times u over root of 1 negative I times p. This is what we have got. Now this is tending towards 0 to infinity, right? 0 to infinity and 0 to infinity. Now what I wish to do is, I would like to multiply both the numerator and denominator by 1 over u. That's acceptable because 1 over u they get cancelled, giving us 1. So this is equal to, now distribute 1 over u inside. So it's going to be 1 over 2i ln of 1 over u comes inside and 1 over u and this u gets cancelled, giving me I over root of 1 negative I times p okay, divided by 1 over u negative I over, that u gets cancelled, so no need to write that, divided by root of 1 negative I times p. So this is what we have got, 0 to infinity. Now the question is, as we are dealing with u tending to infinity, right? So when u is tending to infinity, what can we actually say about it? Is there anything we can say? I want to know what is that we can say. So let me write that as u tends to infinity, 1 over u is going to be moving to 0. So that's an interesting part that we have got. So let me proceed with that. So apply this. This is going to be 0. This is going to be 0. So we are left with 1 over 2 times I ln of I over root of 1 negative I times p divided by negative I over root of 1 negative I times p. Right, the limits, of course I have taken the limits as u tending to infinity, but the lower limit has not yet been applied. Now clearly I can cancel the I root of 1 negative I times p with root of 1 negative I times p. So this is going to give me 1 over 2 times I ln of, I get a negative 1 here. Now we know that, let me write that, we can now apply the all important value of negative 1, e raised to the power of I pi is equal to negative 1. How? Because e raised to the power of I theta is equal to cos theta positive I times sin theta, right? So e raised to the power of I pi, you apply, you get cos of I times pi, right? So this is going to be cos theta. So e raised to the power of I theta is cos theta plus I times sin theta. So e raised to the power of I pi is going to be cos pi positive I times sin pi. Sin pi is off. Cos pi is negative 1. So that's why e raised to the power of I pi is negative 1. This is from complex analysis. So in place of negative 1, substitute e raised to the power of I pi. So that is going to give me 1 over 2 times I ln of e raised to the power of I pi. Now we know a formula, ln of a raised to the power of b is equal to b times ln a. By that, this is 1 over 2 times I. You bring that I times pi over here in front of ln, so you get ln e. You also know that ln e is equal to 1. So this is gone. I can cancel an I and I get pi over 2. So what is the meaning of this? This means this quantity is now pi over 2. But what is this? This is not the entire quantity that we are interested in. We are interested in tan inverse of u over root of 1 negative I times p with pre-multiplied with 1 over root of 1 negative I times p. But we need to know what is the other part of the limit when we substitute 0. Now you substitute u is equal to 0, right? So if I were to substitute the other half of the other part of the limit over here, in place of right, instead of moving towards this, if I were to substitute this quantity for, because I did the multiplication of 1 over u and divided by 1 over u for the fact of handling the upper limit, but for lower limit I don't have to do that, right? For lower limit all I need to do is to just substitute 0 there. So what is exactly this? This is nothing but 1 over root of 1 negative I times p. You substitute the upper limit, so I need to work for the upper limit, tan inverse of u over root of 1 negative I times p. This is for limit u tending to infinity. So to handle this, I did all of this minus limit u tending to 0 of tan inverse of u over root of 1 negative I times p. So this is what we are required. So let me reiterate, to handle this I did this particular alteration or this particular manipulation. So I have got that value. The value that I got is pi over 2. But for here, in this case, I don't have to do anything. I just need to set u to 0. When u is 0, I get tan inverse of 0. Now tan inverse of 0 is equal to 0. So that would mean this gets vanished. Right? So all I am left with for this quantity I1, right? This is I1. Therefore I1 is equal to 1 over root of 1 negative I times P of pi over 2. This is what my I1 is. Now if you were to see our I2 value from here, I2 is also going to be 1 over, the only thing is that I have to change this 1 negative IP to 1 positive I times P with pi over 2 being present there. So I got the I1 value and I2 value. So what we need to do is take I1 and I2 and substitute it over here. So you remember we started I dash of P to be equal to taking I1 and I2, the quantities that I'm showing you here, and you have a quantity of 1 over 2. So we need to consider that. So let me rewrite that. So therefore I dash of P is equal to 1 over 2 times I1 positive 1 over 2 times of I2, which is equal to 1 over 2 times, I'm taking it as a common quantity. Now you need this pi over 2, so let me just place pi over 2 times root of 1 negative I times P positive pi over 2 times of root of 1 positive I times P. Now what I would do is I would just take pi over 2 out and push this 1 over 2 inside, right? So that is done to achieve the solution, right? So let me go to the next page. So therefore we have I dash of P is equal to, as I mentioned to you, I'm going to move this pi over 2 outside and bring this 1 over 2 inside, bring this 1 over 2 inside. So if I were to do that, this is going to be 1 over 2 times the root of 1 negative I times P positive 1 over 2 times the root of 1 positive I times P. So this is what I've got. Now this is my I dash of P, but I need I of P. So for that, integrate both sides. Integrate, let me just push these things off. Integrate both sides. So that would mean the integral operator and the differentiation, they are opposite and they get annihilated. In other words, the neutralization is obtained. So you get I of P is equal to pi over 2 times integral. We will have to integrate with reference to P. So it's going to be dP over root of 1 negative I times P. There is a 2 there. So place the 2 there. Followed by positive, again integral dP over root of 1 positive I times P. There is a 2 there. Okay, so we need to integrate this. So foremost, let me just consider this quantity. Okay, consider integral dP over root of 1 negative I times P. So let me take 1 negative I times P to be equal to some S or S squared. So I differentiate this, I get negative I times dP is equal to 2 times S ds. So you substitute that value in place of dP, you substitute 2 times S ds divided by negative I. So 2 times 2 is taken out, S is retained, ds is placed, negative I is taken out, divided by S squared, root of S squared. So that's going to be S ds integral 2 times I with a negative sign, and S gets cancelled, give me integral ds, which is going to be S. So it's going to be 2 times negative I with the S. But S is nothing but root of 1 negative I times P. This is what we've got. So for this quantity, there isn't going to be much change. The only change is that you will have a positive sign. So if you were to take this as B, so therefore B is going to be, this is equal to pi over 2, substitute the values, is going to be 2 times of negative I root of 1 negative I times p, positive 2 times of I root of 1 positive I times p. So this is what we've got. Now we have an I there, so what we can do is we can take the I out or 2 out. So I think these terms have to be carrying an arbitrary constant c. Now can I take that I out? So I have I got a 2 pi over 2, and I did not take this 2 into account, so there is also a 2 there, so place the 2 there, right? So we need to be careful when we're doing integration of this magnitude. So this 2 has already been placed here because we just considered this quantity without the pre-multiply 2. So the 2 and the 2 and the 2 and the 2 gets cancelled, so I can take the I out. So it's going to be pi over, I place a I, there's a 2 there, so place a 2 there. So this is going to be, if you want, you can start with this first quantity which is positive, 1 positive I times p, and then follow it up with the root of 1 negative I times p. Now you have an arbitrary constant c, and on the left you got I of p. Now let me set p is equal to 0. If p is equal to 0, this is going to be 0, so root of 1, this is going to be 0, so this entire thing goes off. So this would mean I of 0 is equal to c. This means c is equal to 0, right? Because I of 0 is equal to 0. We have obtained it, so that means c goes off. So this means you have I of p is pi over 2 times I root of 1 positive I times p negative root of 1 negative I times p. So this is what we have got, but we are interested in I of 2, right? So therefore p is equal to 2. So when p is equal to 2, you get I of 2 is equal to pi over 2 times I root of 1 positive 2 times I negative root of 1 negative 2 times I. So now we will have to evaluate this, right? Of course, you might say, should we need to evaluate, is it, why not we stop here? But we cannot stop here. We need to evaluate this. We need to see the form, because this is in complex form. Most of the times we will try to get rid of this form. So how do we get this form out? So let me go to another page. Now this is a complex number. 1 positive 2 times I is a complex number. This is of the form x positive iy. Now we will write it in the form of z. So this is actually z. Z is equal to r times e raised to the power of I theta, right? Now r is equal to root of x squared positive y squared. This is going to be root of 1, x is 1, and my y is 2. So this is going to be as 2 squared. So 4 positive 1 root of 5. So this is going to be my r. My theta is tan inverse of y over x. So my y is 2. So we need to get the value of theta, or I would say the argument tan inverse of 2. We need to extract this tan inverse of 2. Now this is what we have got. So we are interested in root of this value, right? So let me just represent this. So therefore z is equal to, where is my r? So root of 5 times e raised to the power of I. My theta, the theta is 2 here, so tan inverse of 2. So this is what we have got. Now if you are going to be taking root of z, this is z, but we don't need exactly z, we need root of z, right? So therefore root of z is going to be root of z is 1 positive 2i, is going to be 1 root of 1 positive 2i or I2, which is going to be square root of 5 e raised to the power of I times tan inverse of 2. Now this is going to be rewritten as root of 5 e raised to the power of I times tan inverse of 2 raised to the power of 1 over 2. This can be further rewritten as root of 5 raised to the power of 1 over 2 times e raised to the power of I times tan inverse of 2 raised to the power of 1 over 2. Now that 1 over 2 can be brought inside, right? So if you were to bring this 1 over 2 is actually moving in. This 1 over 2 is moving in and hitting the components inside. So when you are representing that 1 over 2, because these two are actually the exponents, right? So when you are actually bringing the 1 over 2 inside, this is going to be the form in which you will have to write it. Okay, so you need to be a little bit careful when you are treating quantities of this magnitude, of this fashion, or this form. So having given you this, let me just rewrite this. So this is going to be root of 5 that is present inside the entire root. So this is going to be, we will have to obtain e raised to the power of I times tan inverse of 2 divided by 2. So this is going to be our quantity that we will have to evaluate. So this is just basically for one part, right? We are only dealing with this part, so we will have to deal with the other part also, right? So let me write that down. This is equal to root of 1 positive 2i. So coming to the other part, what would be the other part? So therefore root of 1 negative 2i is going to be root of 5 e raised to the power of negative I times tan inverse of 2 over 2. So this is what you got. So you have to add these two things. I think it's subtraction, right? You subtract here. So therefore I of 2 is equal to pi over 2 times I. This is going to be root of 5 e raised to the power of I times tan inverse of 2 over 2. I can take root of 5 common, so it's going to be negative e raised to the power of negative I times tan inverse of 2 over 2. So this is what we have got. Now I push this 2i inside, so let me retain the pi. Root of 5 is going to be e raised to the power of I times tan inverse of 2 over 2 negative e raised to the power of negative I times tan inverse of 2 over 2 divided by 2 times I. Now this is nothing but the representation for sine z. So pi times root of 5 sine z. So it's going to be sine of tan inverse of 2 over 2. Why did I say sine z? Because that is how the sine z is represented. You can watch the representation I gave when we started with the quest to find out the quantity tan inverse of z. So this is sine of tan inverse of z. But now the all important part is we will have to find out what exactly is this value. That is an important thing. What is tan inverse of z? So I'm going to take, let say phi or theta. You can take anything. I'm going to take theta. Let theta be equal to tan inverse of 2. So this would mean my tan theta is equal to 2. So that would mean this is my theta. So tan theta is opposite over adjacent, right? So it's going to be 2 over 1. So that means hypotenuse side. What is my hypotenuse side? This is going to be, I need to get the hypotenuse side. So it's going to be 2 squared plus 1 squared, which is equal to 4 over 5. So it's going to be root of 5 units. So this is going to be root of 5. So I've got tan theta value which is available, and sine theta is going to be 2 over root 5, and my cos theta value, I can extract the value of cos theta, right? And that would be the adjacent side. That's easily got. So let me do that. Now also from here we know cos theta. Cos theta is going to be adjacent over hypotenuse, so it's going to be 1 over root 5. Now we will have to get sine of tan inverse of 2 divided by 2. So I have taken theta to be equal to tan inverse of 2. So that would mean we are interested in the value of sine of theta over 2. So this is what we are interested in. So for that we will have to utilize our all important formula for cos squared theta. Now let me just change this to cos squared, say sum a. Cos squared a is equal to 1 positive cos 2a divided by 2, and sin squared a is equal to 1 negative cos 2a divided by 2. Now if a is taken to be as, say, sum theta over 2, then this formula is rewritten as sin squared of theta over 2 is equal to 1 negative cos 2 of theta over 2 divided by 2. 2 gets cancelled, giving me 1 minus cos theta over 2, and on the left you got sin squared theta over 2. Now I need to get this value. I need to get sin theta over 2. So that would mean I have sin theta over 2 to be equal to root of 1 negative cos theta over 2. Now cos theta I have found out. Cos theta is 1 over root 5. Substitute that value. So therefore I don't have to directly utilize the value of sin theta. I need to come to this point. Sin of theta over 2 is equal to root of 1 negative cos theta is 1 over root 5. Substitute that divided by 2. So this is equal to, take the LCM, you get root 5 negative 1 divided by root 5. This entire thing is divided by 2. So if you were to flip it, this can be rewritten as root of 5 negative 1 divided by 2 times root 5. So this is the value that you are getting. And what is this? This is nothing but sin theta over 2. And what is theta? We have taken theta to be equal to tan inverse of 2, right? So therefore sine of tan inverse of theta divided by 2 is equal to root of 5 negative 1 divided by 2 times root of 5. Now this is not finished. Now you got to take this value and substitute it over here. So therefore I of 2 is equal to pi times root of 5. In place of this, substitute this value. So it's going to be square root of 5 negative 1 divided by 2 times root of 5. Now this can be rewritten as pi times root of 5 and root of 5 negative 1 divided by root of 2. In fact, I could have placed the root 2 there. It's okay. So it's going to be root of 2 times root of 5. So root of 5 gets cancelled, giving me pi times, I have root of 5 negative 1 divided by 2. Now if I were to take the rationalization, if I were to multiply by, or I would say the best word is to just rationalize. If I were to rationalize this, what is the rationalization factor we can use? Say for example I want to multiply by root of 5 positive 1 and divide by root of 5 positive 1, then this is nothing but a negative b times a positive b, which is a squared negative b squared. In this case it's root of 5 negative 1 times the root of 5 positive 1, which is going to be root of 5 times root of 5 is going to be 5 negative 1, which is going to be 4. So this is going to be pi times root of over here 4 divided by 2 times root of 5 positive 1. 2 can divide 4, so that, let me use this space. So is equal to pi times 2 divides 4 2 times. So it's going to be root of 2 over, I can rewrite root of 5 positive 1 as 1 positive root 5. Now this can be rewritten as pi times, let me write this like this, root of, I'll just place the, instead of writing it like this, let me just place 2 there and 1 positive root 5 there, and I will place the square root like this. And further I want to utilize one more step. This is what we have got. Let me utilize one more step. This is equal to pi times of 1 over, can I write it like this, root of, I need to get, can I write it like this, 1 positive root of 5 over 2, can I write it like this? Yes or no? because if I were to flip it, I would actually getting the 2 in the numerator and the root of 1 positive root 5 in the denominator, right? But can you tell me what exactly is this? Can you think about it? And what is this? This quantity is the golden ratio, and that is represented by phi. And the final solution for I of 2 is pi over root of phi. And that is the end of this particular video. Everybody, please like, share and subscribe to our channel until we meet again. Thank you.